Imagine building a machine in 1977, giving it just enough power to survive a few years, sending it toward the outer planets, and then watching it continue traveling for nearly half a century, farther than any human-made object has ever gone. Now imagine that after all those years, the machine reaches a place no spacecraft had ever sampled directly. And instead of finding a clean border between our solar system and the space between stars, it finds something far stranger. Voyager 1 crossed the Heliopause in August 2012, becoming the first spacecraft to enter interstellar space. And what shocked scientists was not a monster, a wall, or some mysterious object waiting beyond the planets. It was the behavior of the space itself. The plasma was unexpectedly dense. The magnetic environment was strangely organized. Energetic particles suddenly behaved as though a door had opened, and later, Voyager began detecting an incredibly faint, almost continuous plasma signal that allowed scientists to measure the density of interstellar space over an enormous distance. And that discovery changed one of the simplest pictures we had in our heads about the solar system. We tend to imagine the sun as sitting inside a neat bubble with a clear edge, and beyond that edge, everything instantly becomes ordinary interstellar space. Voyager showed that reality is much messier. There is a turbulent, compressed, magnetized boundary region where the influence of the sun and the environment between the stars interact, and that boundary may be one of the most important places in the galaxy for understanding how stars protect their planets. To understand why this surprised scientists, we have to follow Voyager to the edge. Back in 1977, NASA launched two spacecraft that were originally designed for a much shorter mission. Voyager 1 and Voyager 2 were sent on a rare planetary alignment that allowed gravity assists to fling them from one world to another, turning the planets themselves into giant gravitational slingshots. Voyager 1 raced past Jupiter and Saturn, while Voyager 2 went on to become the only spacecraft ever to visit Uranus and Neptune. The original mission was spectacular enough to become legendary, but the really strange part happened afterward. The spacecraft kept going. They passed up beyond the planets, beyond Pluto's orbit, and into a region where sunlight was becoming weaker and the solar wind was spreading thinner. But the sun does not simply stop influencing space at Pluto. It constantly blows a stream of charged particles outward, a flow called the solar wind. Those particles carry the sun's magnetic field with them, creating a giant bubble around the solar system called the heliosphere. Think of it like an invisible cosmic atmosphere, not made of air, but made of plasma and magnetic fields. And just as Earth's atmosphere has a boundary where it meets space, the heliosphere has an outer boundary where the outward push of the solar wind encounters the material between the stars. That boundary is called the heliopause. For decades, scientists could only model it. They could not send a probe there and actually touch it. Then Voyager approached, but the approach was not smooth. Before reaching the heliopause, Voyager 1 entered a region called the heliosheath, where the solar wind had already slowed dramatically after encountering the termination shock. The spacecraft was now traveling through a strange frontier where solar material was compressed and disturbed. And then the measurements started becoming difficult to interpret. In 2012, Voyager 1 detected a dramatic change in energetic particles. Particles originating inside the heliosphere suddenly dropped away, while galactic cosmic rays coming from outside increased to some of the highest levels seen during the mission. That sounded exactly like what you would expect if Voyager had crossed the solar system's protective boundary. There was only one problem. The magnetic field did not behave the way many scientists expected. At the boundary, the strength of the magnetic field changed substantially, but its direction changed by less than about 2 degrees. That was strange. If Voyager had simply crossed from the sun's magnetic environment into the interstellar magnetic environment, scientists expected a much more obvious directional transition. Instead, the spacecraft seemed to be moving through a region where the two environments were interacting in a complicated way. This is where the story becomes much more interesting. The heliopause is not a solid surface. You could not paint a line across space and say, on this side the sun, on that side the stars. It is a dynamic boundary created by competing flows. The solar wind pushes outward, the interstellar medium pushes inward. Magnetic fields thread through both regions. Charged particles move along those fields. And when these ingredients meet, the result is not a simple wall. It is more like a cosmic shoreline, constantly being squeezed, stretched, and reshaped. Voyager 1 gave scientists their first direct measurements from the other side of that shoreline. And one of the biggest surprises was the density. Space between stars is unbelievably thin. So thin that the word empty can feel completely reasonable. But it is not empty. There is plasma, dust, magnetic fields, cosmic rays, and incredibly sparse matter spread through it. Voyager's plasma measurements revealed that the interstellar plasma around the spacecraft was much denser than the plasma inside the outer heliosphere. The difference was dramatic, roughly 40 times higher than the density Voyager had measured in the region immediately inside the boundary. That number matters because density is one of the clues that tells scientists what kind of environment the spacecraft is actually passing through. And Voyager had a remarkable way to measure it. Its plasma wave instrument was not designed as a microphone. There is no air out there for a microphone to carry sound. Instead, the instrument detected oscillations in the plasma, vibrations in the charged particles surrounding the spacecraft. Those waves have characteristic frequencies related to electron density. Higher frequency means more electrons packed into the plasma. So scientists could effectively listen to the plasma and use its pitch as a density measurement. And then something almost poetic happened. Voyager started hearing interstellar space, not sound in the ordinary sense, not something a human astronaut could hear with their ears, but electrical plasma waves that could be converted into audio frequencies. The first major signals appeared after solar disturbances sent shock waves outward from the sun. When those disturbances eventually reached Voyager, they shook the plasma around the spacecraft and triggered oscillations. The instrument detected them. The frequency revealed the density. And suddenly, something that had been invisible for decades became measurable. The space around Voyager was no longer just a theoretical region on a computer model. It was a physical environment producing signals in a tiny machine launched from Earth in the 20th century. Scientists literally had a way to hear the boundary of our cosmic neighborhood. But there was an even stranger discovery waiting in the data. The obvious approach would have been to wait for occasional solar shock waves to pass Voyager, measure the resulting plasma oscillations, and use those events as snapshots of the interstellar medium. The problem was that these events were rare. They might occur roughly once a year. That would give scientists only scattered measurements across an enormous stretch of space. Then researchers looking closely at Voyager's data noticed something much fainter. A weak, nearly continuous plasma wave emission appeared between the stronger events. It was so subtle that it could easily be mistaken for background noise, but after filtering the data, a persistent signal emerged. It behaved like a very quiet cosmic tone, and the tone changed as Voyager traveled. That meant the spacecraft could do something astonishing. It could continuously sample the density of the interstellar medium. Instead of taking occasional snapshots, Voyager was slowly building a long-distance map of the environment beyond the heliopause. The signal suggested that the electron density around Voyager had increased after the spacecraft entered interstellar space and then remained within a similar range, with fluctuations across the data that scientists analyzed. This was not just another measurement. It revealed that the interstellar environment immediately outside our heliosphere was not a perfectly uniform ocean. There were variations, there were waves, there were disturbances. And there was evidence that the boundary itself was affecting the material around it. In other words, the sun does not simply end and then disappear from the story. Its influence extends into the space between stars. That leads to one of the most important ideas from the Voyager mission. The heliopause is not merely a border, it is an interaction zone. The solar wind has spent billions of years carving a cavity through the surrounding interstellar medium. As the sun moves through the Milky Way, its heliosphere travels with it. The exact shape and size of that bubble depend on the strength of the solar wind, the sun's activity, and the properties of the interstellar environment surrounding it. So the solar system is not sitting inside a static shell. It is more like a moving bubble being pushed through a cosmic ocean. And that ocean is not the same everywhere. This matters far beyond Voyager. Because if you want to understand whether a planet is exposed to dangerous radiation, you need to understand the shield surrounding its star. The heliosphere helps block a substantial portion of galactic cosmic radiation from reaching the planets. Voyager observations showed how dramatically the particle environment can change across the heliopause. Inside the heliosphere, solar particles dominate much of the environment. Outside it, galactic cosmic rays become much more prominent. That means the heliosphere is part of Earth's larger cosmic environment. We are not protected only by Earth's atmosphere and magnetic field. We are also living inside a bubble produced by our star. And Voyager was the first spacecraft to cross that bubble and tell us what was happening on the other side. But there was another surprise. Scientists had expected the magnetic field in interstellar space to point in a direction that could be compared relatively cleanly with the magnetic field just inside the heliosphere. Instead, Voyager's measurements showed a complicated relationship. The magnetic field immediately outside the heliopause appeared to be influenced and distorted by the solar wind. The field was not simply an untouched interstellar magnetic field waiting beyond the boundary. It was part of a transition region that helped explain why some early measurements seemed to disagree with expectations. Voyager was not necessarily sampling pristine interstellar space. It was sampling interstellar space that had been disturbed by the sun. Imagine standing beside a river and trying to measure the natural current, only to discover that you are actually in a zone where the river is colliding with another flow. The water is real, your measurement is real. But the environment is not simple. That is essentially what Voyager found. And this is why the phrase edge of the solar system can be misleading. There is no cliff. There is no invisible glass wall. There is a transition where different physical systems collide. And this is where the story becomes relevant to worlds far beyond our own. Our sun is not unique. Other stars produce winds. Other stars have magnetic fields. Other stars move through interstellar space. And if they have planets, those planets may sit inside their own stellar bubbles. Some bubbles could be larger. Some could be smaller. Some could be compressed by denser interstellar environments. Some could be shaped by powerful stellar winds. The boundary around a star could therefore influence the radiation environment experienced by planets orbiting that star. Suddenly, Voyager's strange measurements are not just about two old spacecraft. They are helping scientists understand the invisible space around stars throughout the galaxy. Voyager was never designed for this kind of mission in the way a modern interstellar probe would be. Its technology comes from the 1970s. Its computers are extraordinarily primitive by modern standards. Its radio transmitter operates with a tiny amount of power compared with what we take for granted today. And yet it is still communicating across tens of billions of kilometers. The signal is incredibly weak by the time it reaches Earth. Engineers use the Deep Space Network to receive it. And every piece of scientific information that comes back has crossed an enormous distance. When Voyager 1 reports a plasma wave, a magnetic field measurement, or a cosmic ray event, scientists are not looking at a simulation. They are reading a direct measurement from a machine traveling through the environment beyond the heliosphere. That is why the Voyager mission is so scientifically unusual. It is not merely a telescope looking outward. It is a probe physically moving through the space it is studying. There is a profound difference between seeing a distant environment and being inside it. A telescope can tell you what another star looks like. Voyager can tell you what the plasma around our star actually feels like to a scientific instrument, and the farther it travels, the more valuable that becomes. Because the spacecraft is gradually moving away from the region most strongly influenced by the sun. Scientists expect that farther out, Voyager will sample a more pristine interstellar medium. That could help separate the effects created by the heliosphere from the properties of the space between stars itself. Think about what that means. The same spacecraft that left Earth in 1977 is slowly moving from the Sun's neighborhood into the larger galactic environment. It is crossing from one physical regime into another. And it is doing it at a speed of roughly 17 kilometers per second relative to the Sun. That sounds fast until you remember how enormous interstellar distances are. At that pace, Voyager is not going to reach another star anytime soon. Its mission is something different. It is becoming a time capsule of the environment around our solar system. And every measurement adds another piece to a map that no human had before. There is also an important correction to the popular idea that Voyager has completely left the solar system. Scientists often use different definitions of where the solar system ends. If you define the boundary by the heliosphere, Voyager 1 and Voyager 2 have crossed it. If you define the solar system by the Sun's gravitational influence, the story is very different because the Oort cloud is thought to extend vastly farther out. So Voyager has entered interstellar space in the sense that it is outside the Sun's heliosphere, but it has not suddenly escaped every influence of the Sun. That distinction is crucial. The real discovery was not that Voyager found a final edge. It found a boundary between environments. And that boundary was far more complicated than the simple picture scientists once imagined. Now return to the strangest clue of all, the faint plasma tone. Imagine the spacecraft moving farther and farther away, with no visible landmarks, no planets, no moons, and almost nothing that a camera could photograph. Yet the instruments detect an almost continuous whisper in the plasma. The frequency changes, the density changes. The environment changes. And from that tiny signal, scientists can infer what the invisible medium around the spacecraft is doing. It is a reminder that space is not silent. It is full of electromagnetic waves and plasma oscillations that our ears cannot normally hear. To Voyager, those waves are not music, they are data. To scientists, they are a way of turning an invisible environment into something measurable. And that may be the most astonishing thing Voyager detected at the edge of the solar system, not an alien structure, not a mysterious planet, not a physical wall, a living, changing boundary between our star and the galaxy, a region where the Sun's influence and the interstellar medium collide, a region dense enough to reveal itself through plasma waves, a region where cosmic rays surge as solar particles disappear, a region where magnetic fields become tangled in a way that forced scientists to rethink what crossing the heliopause actually means, and a region that appears to protect the planets from a large fraction of the harsh radiation traveling through the galaxy. The Voyagers have therefore done something no laboratory on Earth could fully reproduce. They carried instruments into the natural interface between a star and interstellar space. They crossed it, they measured it, and they kept going. Today, both spacecraft continue their long journey, although their available power and scientific capabilities are gradually declining as their radioisotope power systems produce less energy. NASA has already had to turn off instruments and manage power carefully, choosing which systems can remain alive as the spacecraft age. Yet the surviving instruments continue to send back information about magnetic fields, particles, and plasma waves. Every year, the spacecraft move farther away. Every year, the signal becomes harder to work with. And every year, the scientific value of those measurements becomes harder to replace. Because there is no backup Voyager waiting nearby. There is no second probe already parked at the Heliopause. For now, these two ancient spacecraft remain our only direct messengers sampling interstellar space from within the environment of our own stellar neighborhood. That gives their strangest discovery a deeper meaning. The edge of our solar system is not an edge in the ordinary sense. It is a frontier, and frontiers rarely behave like lines on a map. They are messy, they are dynamic, they are shaped by competing forces, and they often reveal that the world beyond them is connected to the world behind them. Voyager crossed what we once imagined as a boundary and discovered that the Sun's influence does not simply switch off. It fades, interacts, compresses, distorts, and leaves signatures in the plasma and magnetic field far beyond the planets. The solar system is not an isolated island floating in darkness. It is moving through the Milky Way. surrounded by an interstellar environment that pushes back and leaves fingerprints on the bubble created by our star. And somewhere out there, billions of kilometers beyond the planets, a small spacecraft built nearly 50 years ago is still moving through that transition. Its computers are ancient, its power is fading, its signal is barely whispering across the darkness. Yet that whisper is telling us something profound. The boundary of home is not a wall. It is a conversation between a star and the galaxy. And Voyager is the first machine humanity ever built that went close enough to hear it.